Hi, good to see you all in here with a new topic in the social media platform. So I'm Aiswarya, Assistant Professor in the Department of Biomedical Engineering and Immunology College of Engineering. So let's begin the topic. So today's topic is Parsevels Theorem. Okay, as we are all familiar with signals and systems, so this topic comes under mathematics and both signals and systems. So now I'm going to take something about signals and systems. So actually, Parsevels theorem, which means it establishes a fundamental relationship between the time domain and the frequency domain representation of a signal. So it established the fundamental relationship between a time domain and a frequency domain. Both it creates a definition, a relationship between the time domain and the frequency domain. Actually, what does it states is that the total energy, that is maybe it's power, maybe a periodic signal, or maybe the energy signal. So total energy of a signal in the time domain frequency is equal to the total energy or the total power in the frequency domain. So it gives a relation between the time domain and the frequency domain. So in the time domain, if it has the power, then in the frequency domain also it is equal to the total power. If in the time domain it has the energy, then it is equal to the energy of the frequency domain. So this is as well as states that the total energy of the signal in the time domain is equal to the total energy in the frequency domain. So the key points, that is, it works for aperiodic energy signals and periodic power signals. So as it denotes, it works for aperiodic, that is, it works for energy signals and the periodic power signals. So when it works for the energy signals, it works for aperiodic, and when it works for power signals, it works for periodic signals. So as we have already know what is periodic and aperiodic, which satisfies the signal condition is called as periodic, and when it does not satisfy the signal condition is called as aperiodic. So as per when it is used, it is really useful in signal processing, communications, and spectral analysis. So communication process also, signals and systems are very important, as because it is used for the communication channel between the transmitter and the receiver. So the signal processing is the process between the signals and systems, and also digital signal processing. So that both combines to form the signal processing. Again, spectrum analysis or spectral analysis that is used to analyze the spectrum. Spectrum which denotes for the amplitude of the signal. So it is useful in signal processing, communications, and spectral analysis. Again, directly related to Parsevels theorem. Parsevels theorem, which generalizes the concepts to inner products in Hilbert spaces. So what does it mean by Parsevels theorem? P-L-A-N C-H-E-R-E-L-S, Parsevels theorem. So it is actually related to Parsevels theorem. What does that mean? It is a simultaneous generalization of the completeness of Fourier series and Parsevels theorem for the real line. It is actually related to the Parsevels theorem, which generalizes the concept of inner products in Hilbert spaces. So what is actually the Parsevels theorem is the simultaneous generalizations of the completeness of the Fourier series and the Parsevels theorem for the real lines. That is the Parsevels theorem, which is generalized to the concept of inner products of Hilbert space. What is Hilbert space? Hilbert space is an abstract vector space that extends the geometry of ordinary Euclidean space into finite or infinite dimensions, featuring an inner product and completeness. So that is what Hilbert space. So the inner products of Hilbert space is related to the Parsevels theorem. So the Hilbert space is an abstract vector space that extends the geometry of the ordinary Euclidean space into finite or infinite dimensions, featuring an inner product and completeness. So the core properties for the Hilbert space mean a vector space, inner product, and a completeness. So by these conditions, only when these 4 points are the core properties get satisfied, then the Parsevels theorems will generalize with the Hilbert space. Okay, what are they? Vector space, inner product, completeness. So the main uses of using this Hilbert space for the generalization of Parsevels theorem is according to the Parsevels theorem, the main uses is quantum mechanism, signal processing, mathematics and data sciences. As I have already told you, quantum mechanics, what that serves as the fundamental mathematical frameworks where quantum states, wave functions and probabilities lives. Okay, serves as the fundamental mathematical framework where quantum states, wave functions and probabilities live. And for signal processing, how does it treats? It treats sounds, wave, radio signals and images as vectors to filter noise and analyze frequencies. Only by this method, signal processing can be used. Again, for mathematics and data science, so underpins advanced calculus, differential equations, and kernel methods in machine learning can be used into this mathematics and data science processes. Okay. So this Parsevels theorem is defined as A is equal to minus infinity to infinity p of t dt is equal to 1 by 2 pi integral minus infinity to infinity modulus of x of omega the whole square d omega. So this is the Parsevels theorem which we have to need to prove. So the first graph shows that time versus power signal, and the next one is the frequency with the energy. So power is calculated in watt and energy is calculated in joules. Okay. So the instantaneous power for the time domain plus spectrum will be like this. It comes gradually highs and rises to the maximum level and then gradually gets reduced. That is the instantaneous power for time domain between the time and power. So the next one is energy spectrum between the energy frequency, which is joules. That is gradually reduced. It rises immediately and reaches the top point and gradually reduces. That is the energy spectrum for frequency domain. Okay, so the Parsevels theorem equation is E is equal to minus infinity to infinity p of t dt is equal to 1 by 2 pi integral minus infinity to infinity modulus of x omega the whole square d omega. So Parsevels theorem states that the continuous time signal x of t, the energy in the time domain is equal to the energy in the frequency domain. So that is what Parsevels theorem's exact statements. So Parsevels theorem states that for a continuous time signal, the continuous time signal here is differential is mentioned as x of t. The energy in the time domain, the energy in the energy domain is equal to the energy in the frequency domain. The energy in the time domain is equal to the energy in the frequency domain. That is given as integral minus infinity to infinity modulus of x of t the whole square modulus closed dt is equal to 1 by 2 pi integral minus infinity to infinity modulus of capital X of omega the whole square d omega. The dt is the time domain and omega is the frequency domain. So where capital X of omega is the Fourier transform of x of t. So see, the left hand side you have small x of t and the right hand side you have capital X of omega. So what is actually x of omega? The capital X of omega is actually the ft of small x of t. Ft means Fourier transform of the small x of t in the energy domain. Okay. So see how the signal is reconstructed in the sequence time systems using this Parsevels theorem. There is a given signal which is again converted using the Fourier transform, and then the signals out from the Fourier transform is filtered using filtering technique. Then it is given to inverse Fourier transform where x of t will becomes x inverse of t, and then it gives the a reconstructed signal. The original signal is reconstructed into a reconstructed signal using Fourier transform method, and after the filtering process it will again goes into inverse Fourier transform method to form the reconstructed signal. Okay, so this is what already told. In signal processing, the signal can be analyzed in time domain and in the frequency domain. So as for the time domain, the amplitude will be as amplitude versus time, and as for frequency domain, the amplitude versus frequency. This is the actual term included in the graph itself. So let me ask you a common question. Does the total energy of the signal will change when the representation in the frequency domain? Once again, does the total energy of your signal change when represented in the frequency domain? Exactly no. The Parsevels theorem always states that the total energy of the signal remains the same in both the time and frequency domain. That is left hand side equal to right hand side. So there is no change. Okay? Okay. So as per the equation minus infinity to infinity x of t the whole square dt is equal to 1 by 2 pi integral minus infinity to infinity modulus of capital X of omega the whole square d omega, where the small x of t will represent the time domain signal and the right hand side capital X of omega represented the Fourier transform of x of t. Okay. So the meaning is the left hand side, that is the energy in the domains time domain, and the right hand side of the equation energy in the frequency domain, both are equal. So what is the interpretation here? The theorem shows that the signal energy is conserved. The theorem already shows that the signal energy here is conserved, that is used or preserved or stored. The Fourier transform only changes the representation. The right hand side, the Fourier transform of the left hand side will only changes the representation. Just it changes the representation. That is, in the left hand side it is represented as small x of t, and in right hand side it is just represented as Fourier transform, that is capital X of omega. Only the representation varies, nothing differs there. So it does not increase or decrease the energy. So what happens here? The energy does not decrease or increase. So for your best understanding, let me give an example. A 500 rupee note, okay, remains 500 whether it is in your wallet or in your bank account, isn't it? You have a 500 or 1,000 or 2,000, something like that. If the amount is in your wallet, in your purse, or in your bank account, the value is same, isn't it? Yes. Only the form changes, not the value, isn't it? Yes. Only it is in the form of bank or it is in your wallet. Only the form changes and not the value. As like that, only the representation changes. That is, the small x of t will changes into capital X of omega. Only the form changes, but not the value. See, now let me explain you about this. See, this is the equation I have told you, isn't it? See, this is the minus infinity to infinity x of t dt is equal to 1 by 2 pi minus infinity infinity x of j omega the whole square d omega. So what does it represent? X of t or x of j omega, both represents same. There is no change in the value. Only the no change in the value, only the form gets changed. Okay. So see proof. E is equal to minus infinity into modulus of x of t the whole square dt. Again, it is given as x of t, the modulus of x of t the whole square is represented as x of t into x star of t dt. So what is actually the x of t and x star of t? It is represented in the right side, okay? X of t value is given here, that is 1 by 2 pi minus infinity x of j omega e power j omega t d omega, and then x star of t. The value is also given 1 by 2 pi minus infinity x star of j omega e power minus d omega t d omega. Okay, now what happens here? See here, x of t and x omega t value should be substituted. That is, x of t is represented as x of t, no changes. But x star of t has to be noted here. That is 1 by 2 pi minus infinity x star of j omega e power minus d omega t d omega into this dt. Okay, it is mentioned here. So again, minus infinity into this much of term has to taken out. Okay, this term has to be taken out as adjustment. So it is taken out and the remaining is written here. So the remaining this much term is calculated as which one? 1 by 2 pi infinity minus infinity x star of j omega and j omega, and this much term is also calculated as x of j omega. How much? This much term. This much term is denoted as x of j omega into d omega. Again, this x of x star of j omega into x of j omega is calculated as which one? Modulus of x of j omega the whole square, okay, by d omega. So hence, see, the right hand side is achieved. So it is proved. Okay. So as per the application, there are many applications, the real-time applications, wherever the signal processing can be used. That is, in signal compression, Parsevels theorem ensures that the energy of a signal is preserved during compression. Only it is preserved during the compression technique. Then signal denoising, what is that? The theorem helps in evaluating the energy of the noise and the signal, which helps in evaluating the energy of the noise and the signal, facilitating the design of denoising algorithm. For designing the denoising means without noise. For that algorithm, this signal denoising theorem is used. Then also it is used in DSP. DSP means digital signal processing. Again, it is used in communication systems. It is used in audio processing. Again, it is used in image processing. Again, it is used in power spectrum analysis. Also, it is used in power spectrum analysis, as I said, first of all. Then it is also used in wireless communications. Now it is used in radar systems. The signal systems are widely used in radar systems. Okay, so the radar system is one of the most basic things which is used in the ISRO, BSNL. So everywhere it is used. Hence, the signal system is one of the main topics in all the competitive exams. So advantages, as for advantages, It simplifies energy calculations. Okay, simplifies energy calculations. It confirms energy conservations, and also it is useful in Fourier analysis. Okay, it is used in Fourier analysis, and it is essential in communication engineering. Okay, it is also used in communication engineering. Then, as per the advantages, it also has limitations also. Okay, so applications only applicable only when the signal has finite energy. It is only applicable when the signal has finite energy, and it requires a valid Fourier transform. Okay, it requires a valid Fourier transform. Also, not directly applicable to power signals. So it is used in energy power signals, but it is not directly used in power signals. Okay, if we're using certain variations, it is used in power signals, but it is not directly used in power signals, but it is directly used in energy signals actually. Okay, so actually, Parsevels theorem states that the total energy of the signal is the same in both the time and frequency domains, as we have explained first of all itself. Then it provides a bridge between time domain frequency domain analysis. So for analysis in the time domain and the frequency domain, both can be equal. So it can act as the Parsevels theorem, which acts as the bridge between the time domain frequency domain analysis. Also, it is important theorem in signal sense systems and in digital signal processing. That is what both combined called the signal processing. So it's very much important in both. Okay. So I hope you all understand my section. So please do like the video, and if you have any doubt, please do comment. Okay. Thank you.